So it's a great pleasure to welcome Andrés Reyes Lega to give today's seminar. He's going to tell us about geometric phases for quasi-free fermions at finite temperature. And I hand it over to you.
Okay, then Joe. So thank you very much for the invitation. I am quite happy to be able to talk about my work to you. So what I am going to do is to first try to frame the talk in the context of the work I have been doing, and just explain a little bit about my motivations. Then I will go to a more formal part where I will describe a certain kind of C mod 2 index, which is suitable to study fermionic systems. And then I will go to the third part of the talk, where I will explain something we have been trying to do, trying to extend this use of topological classification of phases of matter for systems at non-zero temperature. And this will involve the application of a kind of generalization of the geometric phase for thermal states. So first, let me just acknowledge my collaborators. So this is part of what I am going to present here was done in collaboration with Javier Buitrago-Asa, who was a postdoc here at our department, and Sebastián Calderón, Link Sequera, and Soat Taban, former students from our group. Well, so as for the motivation, well, nowadays we have been studying topological insulators, which display very exotic phases of matter. And it is quite interesting to see how topology and geometry, I mean, are every time more relevant to the study of quantum systems. So there are different ways of studying these systems. And we have a periodic table classifying different phases of matter according to the type of symmetry and so on. And well, from the point of view of mathematical physics, K-theory, operator algebras, ideas coming from non-commutative geometry, they have proven to be quite useful in this classification. Now, when I got interested in this kind of systems, that was like 10 years ago or a little bit more, I started studying spin chains. And at the time, there were certain papers where the quantum phase transitions that some spin chains display were being studied using geometric phases. So this is how I started working on this. So my motivation came from the study of quantum phase transitions. So I wanted to somehow get an idea of how to study quantum phase transitions using geometry and topology. And then during that time, well, the topological insulators became very popular. So I started digging the literature and trying to find, well, what could be done. And then around 2014, I found works by Araki, by David Evans, who is here, and other people like John Lewis, Matsui. So then I was surprised. I mean, for me, it was a huge surprise to see that the classical Ising model could be described in terms of a topological invariant. No? So then I started to study that index, and well, that became part of the kind of work I am doing now. So for that reason, I have written here this formula, which I will explain during the talk. And this is a very nice formula because it allows, for instance, in the case of the Ising model, to tell apart the two phases that the classical model displays. Now, for me, this has this has a very important consequence when we compare it to what has been done with topological insulators, namely that the classical Ising model is, well, a classical model. It displays a thermal phase transition, and contrary to what one would expect naively, there is a topological invariant labeling the faces, no? So that is a strong motivation for my work, as I will try to explain below. So now let me come to this typical diagram of a system displaying a quantum phase transition. So let us suppose we have some parameter. It could be pressure, could be an external field. And if there is a quantum critical point, well, we could have several situations. One of them is one where there is also a thermal phase transition, which is this, represented by this colored line. But I mean, it is not necessary that there is a thermal phase transition. There could only be a quantum phase transition. In any case, there will be a so-called quantum critical region, which survives at higher temperatures, and which is very useful experimentally because it can tell you about the kind of correlations or kind of phenomena that you would have at zero temperature, which is not achievable in real experiments. No, so my main motivation has been to study such systems and to ask the question whether it is possible to use tools from topology or geometry to learn a bit more about this kind of diagram. So now let me come to the C2 index, no, in the context of quasi-free fermions. So I will start, this will be a bit formal part, and in the third part I will try to illustrate this with explicit examples and then discuss the geometric phase aspects. So when we study fermions, which are non-trivial from a mathematical point of view, but simple enough that we can solve them and study interesting physical examples, then we can consider Hamiltonians, which are quadratic in the fermionic operators. And for that kind of Hamiltonians, which we can regard as a kind of mean field approximation to more complicated models, there is a formalism which is called the self-dual formalism, which is very convenient because it allows us to solve the diagonalization problem for these quadratic Hamiltonians. It can also be applied to systems with interactions, but this is not something I will be able to discuss today. So the idea is to have commutation relations which resemble the usual fermionic commutation relations, but we have an additional structure. So we start with a Hilbert space and a conjugation gamma, which is an antilinear, anti-unitary operator. It is an involution. And then we can construct, given these two structures, the inner product and the conjugation, we can construct an algebra which satisfies, I mean, it can be given in terms of generators, a set of generators and relations satisfying these anti-commutation relations. These appear to be the car relations, but they are not because of this second condition. No, so in practice, there is a way of relating the two of them. So we can construct, one can construct an isomorphism between this self-dual algebra and the usual car algebra. But this setting is more convenient for certain purposes. So so now we have a definition of what a basis projection is. So a basis projection will be an element, a bounded operator satisfying this property, which is just if we apply the conjugation in this way, we obtain the orthogonal projection. And now it can be shown easily, no, that if we act with the conjugation on the rank of the projector, you will get the orthogonal to this projection. So let me call HP the image of the projection, then the image under gamma will be the orthogonal space. And this allows us to decompose the original Hilbert space as a direct sum of the Hilbert space HP plus its conjugate or its orthogonal complement. No? And in this way, we come to something which looks quite close to the formalism of Nambu, no? Which is also used in this context to solve this type of problems. Now, if we have such a basis projection, then we can decompose our generators into what could be called creation and annihilation operators. So what is the purpose of introducing these projections? If we start with a quadratic Hamiltonian, which is not already diagonal at the outset, the problem of finding the ground state can be solved by finding a suitable Bogoliubov transformation. So in this language, we are not committing to using a given ground state, because we don't know what the ground state is. So we keep all possibilities open, and we can in this way describe all possible forms of fermionic operators by changing this projection. So in the end, it will turn out that the diagonalization of such a quadratic Hamiltonian is equivalent to finding a suitable basis projection. So that's the reason for introducing this definition. Now, in this setting, a Bogoliubov transformation will be just a unitary operator which commutes with the conjugation gamma. And such a Bogoliubov transformation, such a unitary operator, will naturally induce an automorphism of the algebra just by using this as the definition for the generators and then extending it. Another fact which is important is that if 1 minus u is a trace class operator, then its determinant can be defined and computed, and it has to be it can only be plus or minus 1. And this will be important for the definition of the index. Now, once we have our operators and we want to define Hamiltonians in this setting, which we can think of second quantized versions of one particle Hamiltonians. So let us consider a bounded operator, a bounded self-adjoint operator H. So we can just take matrix elements for a given orthonormal basis, like as you see in this expression, and then we can define an element in the self-dual Kerr algebra, which I am denoting with this bracket notation. This will be an element in the self-dual algebra, and it represents the second quantization of this operator H. No? So it is basically a quadratic Hamiltonian. So one can see that, for instance, that if H would not be self-adjoint, then it would have to satisfy this property. So this allows us to call this a self-adjoint element, no? When H is self-adjoint. And the set of all these operators will be the set of bilinear Hamiltonians. Now, there is a particular class, which is the one we are interested in, which are called the self-dual Hamiltonians, and they have to satisfy this property. So where does this property comes from? If we start with a Hamiltonian written in terms of fermionic operators, or the usual fermionic operators, then we can have combinations of several types, so combinations of the form A dagger A, but we could also have combinations of the form A dagger or AA. So when one studies such types of Hamiltonians, then the diagonalization problems simplifies if one doubles the Hilbert space, and in that way we introduce a kind of redundancy in the description of the problem. So the Hilbert space gets duplicated, and then the spectrum also becomes symmetric with respect to zero. No, so in this formalism, all of this has been already encoded in the conjugation, and this relation reflects the fact that the spectrum will be symmetric with respect to the origin. And then a projection that diagonalizes the Hamiltonian will be a projection which satisfies this property. So once we have found a basis projection fulfilling this property, we basically have solved the diagonalization problem. Okay, now we have a Hamiltonian that we can induce a dynamics. So in this case, these dynamics will be quite simple in the sense that we have a good control over what is going on. So for instance, if we define these exponential elements, the unitaries, we can define a family of automorphisms, and they will be, we can just think of them like the second quantization of the time evolution in the one particle Hilbert space, which is this one. So we can induce a time evolution. Now, for this particular type of states, I mean, for this particular kind of dynamics, one could ask what are the possible ground states. So the ground states will be of the following types. So here I am using the algebraic notion of state as a functional on the algebra, and we define a quasi-free state to be a state which basically fulfills the statement of Wick's theorem. No? So for odd products of operators, we get 0, and for even ones, we get a combinatorial formula in terms of 2-point functions. No? So we have this definition in terms of a Pfaffian because, well, this is the self-dual version.
Andrés,
yes.
One moment. There is some background noise coming. Somebody is speaking at the background. I don't know from where.
Okay. I don't see.
It may be
right
somebody
now.
else. No, it may be from someone else who is in the audience.
Okay.
I think
It
maybe
doesn't seem to come from
can,
here. Yes.
Then you can control it.
Okay. Is it gone now?
No, I think it's from your microphone. It's either the only two that were unmuted there a second ago were Andrés and Bals.
Are you getting that noise still?
Yes, it seems to be a slight flaw in your microphone.
Okay, let me try to switch to the loudspeaker if it works, okay?
Sure.
So is it okay now?
Yes.
Makes a difference, yeah.
It is gone.
Okay, so yes, perhaps it was a problem with the headphones. So I will just go like this. So I was talking about this family of quasi-free states. So these quasi-free states can be defined in terms of a class of operators that we call symbols. These are positive operators fulfilling this inequality, so between 0 and 1, and they have to fulfill this property, no, with respect to the conjugation. Then, if we have such an operator, we can define a state given here in terms of the 2-point function in this way. This can be extended to a state over the full algebra, and it will be a quasi-free state. Now, there are two types of states which are of interest for us here. One of them is states which correspond to ground states of Hamiltonians, and the other one is symbols that define thermal states for the systems we are interested in. So I will discuss mainly the ground state case, but then towards the end of the talk, they will reappear in the context of geometric phase. So as for the definition of a ground state, then if we have a Hamiltonian, then this Hamiltonian will induce a derivation in the algebra, which I call delta. Delta can be thought of just as the commutator of h with a, modulo a constant. And well, one has to work out what the domain of that derivation is. But in this algebraic language, then the condition for a state omega to be a ground state can be written in terms of this inequality. No, so it is quite convenient. No, and we are going to be interested in studying these ground states. So now let me consider a Hamiltonian, which is a self-dual Hamiltonian. Then using the spectral decomposition, because of the self-dual property, we see that the action of this conjugation on the spectral projections works in this way. No? So it is reflection invariant, so to say. And then we can work with the projection corresponding to the positive part of R, to the negative part, and the projection to 0. Now, because of the property we have on the left-hand side, it turns out that if the Hamiltonian is gapped, so if there is a gap, then this projector E0 will not be there, and then E plus and E minus become self-dual projections. No? So this is important because if we start with the Hamiltonian and we are able to know what this projection E plus is, then we basically can write down what the ground state is. No? So this projection will give us the ground state. So here,
okay. Andrés, isn't it quite restrictive to insist that it's self-dual?
Well,
that H is equal to minus gamma.
Yes, I mean, it
H.
would seem like that, but the class of Hamiltonians I am working with, they are, you can think of BCS-like Hamiltonians, no? So quadratic Hamiltonians in the fields. So they are fairly general. Now, the point is that these Hamiltonians can be rewritten in the language of the self-dual algebra, and there the spectrum becomes symmetric. But I mean, the actual spectrum is just half of it. So this duplication of the Hilbert space comes about because of the diagonalization problem. So there is no restriction in that.
Sorry, I missed where you doubled it then.
Because I started, I mean, since I started with the self-dual approach, we are not seeing that, no?
Okay.
But
so
there is a way.
So you're thinking of taking a Hamiltonian and adjoining to it minus gamma H gamma.
Mm-hmm. So
you get to,
yes,
as you're doubling.
Yes, so you can think in the following way. If you have a usual quadratic Hamiltonian, you would have terms of the following form: A dagger A, which are like H invariant terms, but you could also have let's say superconducting terms of the form A or A dagger.
Yes, absolutely, yeah.
So if you want to write this as a quadratic form in the fermionic operators, you would get a kind of a block matrix operator, no? And then it is quite useful to try to diagonalize directly that operator. So this is where the Nambu space comes in. And when you do that, you have to double the Hilbert space. So let us imagine that you generate one particle states out of the vacuum by acting with A dagger operators, with creation operators. But then the annihilation operators would act to the left on the vacuum, and they would generate dual vectors. So then you take the direct sum of those two Hilbert spaces, and you have a doubled Hilbert space.
Yes, okay.
When you do that, then the Hamiltonian that you get, it has this property. So you have not lost information, so to say. Okay, so, but now the point is that this projection E plus will be a basis projection, and you can characterize the ground state in terms of it, or no, assuming that we have a gapped Hamiltonian. So since we are interested in families of Hamiltonians and in the concept of quantum phase of matter, then there is more or less an agreement that if you have Hamiltonians which or perhaps better said, a family of Hamiltonians that depend on some parameter. Here, I am using S for that parameter. Then, as long as the gap remains open, you could define these Hamiltonians to belong to the same phase of matter. Now, in the context of topological phases of matter, or topological insulators, and so on, you have to include another condition, which is that these Hamiltonians respect the symmetries. No? So you would say, if you have time reversal invariance, you would need to keep that property all along this path. But here I am not using, I am not assuming anything else about symmetries. Now I have been informed by Chris Bourne during some lectures he gave last year that there is a way of considering or regarding this C2 index as a primary object, and all other symmetry classes can more or less be derived out of this one. So we will just, for the sake of this work, consider phases of matter without additional symmetries to be given by these path-connected components. So the idea is to consider a path of Hamiltonians which should satisfy certain properties, like being differentiable in a suitable sense, so that we can consider this flow of Hamiltonians, so to say. Then what we have done technically has been to consider these Hamiltonians to be defined on a lattice. And what we do is to consider restrictions of these Hamiltonians to finite sublattices in such a way that we can control the limit when the lattice grows to the full infinite size lattice. No, so there are some assumptions on the way these limits behave. No, but given that, then we can define this C2 index, mode 2 index, in the following way. Since these basis projections characterize the ground state of the Hamiltonians, let us compare two of these Hamiltonians. Each one of them will have a ground state characterized by a basis projection. Now, if the difference between two basis projections, this is a general definition, if the difference between two basis projections is a Hilbert-Schmidt operator, then the dimension of this space, which is I have to explain this, this wedge symbol means that you have to take the image of the first projection, the image of the second one, or the complement of the second one, and then intersect these images. This will give a vector space. Now, if the difference is Hilbert-Schmidt, this Hilbert space will be of finite dimensions. So you can compute the dimension, and according to whether this dimension is even or odd, you will get a number which is plus or minus 1. So this is the index I was telling about at the beginning of the talks, which, as far as I know, was first introduced by Araki and Evans in the year 83. And they used that index in order to characterize the phase transition of the classical 2D Ising model. But this index has many applications. So one of them nowadays in the context of topological insulators. And as I will show in an explicit example now, this index is the same one that Kitaev introduced while studying his chain, the Kitaev chain. So I will come to that in a minute. So we have the following result now. We are interested in studying these paths of Hamiltonians, which are paths of gapped Hamiltonians. So there is an important assumption about the gap. It was, well, so here, no, the Hamiltonians must be gapped. If that is true, then one can connect these two Hamiltonians along this path by means of automorphisms that are generated along the path. And these automorphisms will be Bogoliubov ones, no? And then it is possible to show that the index has to remain constant all the way through the Hamiltonian. Now, this might not seem like a very new thing to do, but the way we have done it could be useful in order to study generalizations to interacting models. No, it is I think a very difficult problem to define topological invariance, which allows us to classify phases of matter when there is interaction, when there are interactions. So the way we have done it can be thought of as a first step towards trying to generalize it in the interacting case. So, well, the idea is that if we start with the Hamiltonian, for instance, corresponding to the starting point of the path, then one can construct a unitary operator that connects this one to the Hamiltonian at the point S. Now, you will see in the third part of the talk that these operators somehow resemble what we do when we compute geometric phases, because what we have there is a path of Hamiltonians. And well, usually when we discuss Berry's phase, we think about diagonalizing each of these Hamiltonians along the path, and this will produce a line bundle, for instance. No? So we can talk about the parallel transport along the path. But there is a for me, more interesting way of thinking about it, which is this geometry, this bundle structure that appears when we discuss Berry's phase, can be also described in terms of the projections, no? So the spectral projections of the Hamiltonian. So somehow these unitaries are related to these spectral projections, and this, I think, can be important in the temperature, in the non-zero temperature case. So in any case, the statement is that we will be able to construct such unitary operators, and these operators satisfy a certain differential equation. I will show it in a moment. Now, the automorphism that allows us to connect the two systems will be an inner automorphism. And if we compute the corresponding, what we call a relative index, so the index corresponding to projections at two different points, it will have to be 1, meaning that we remain in the same phase of matter according to our definition. So the proof, I will just sketch.
Just to clarify, when you had the subscript infinity there, is that referring to the continuum limit, or I missed?
Yes, no, it's not the continuum limit, but like the thermodynamic limit. So here,
it's the thermodynamic limit. Yeah, okay.
Yes, so we have Hamiltonians defined on sublattices, so like the restrictions of the Hamiltonians to sublattices, and then you start letting the lattice size grow and grow.
Yes,
so infinity refers to the system on the full lattice. No.
Okay.
So we have I will just sketch the idea. The full work is on this.
And just to be clear, why did you need to take that limit first? What goes wrong if I just work with L all the way here?
I mean, in principle, this index can be defined in terms of the full. I mean, on the thermodynamic limit, it is possible to do that. But when it comes to consider interactions, it will be important to have control over the subsystems, no? So corresponding to local lattices.
Sure. Okay. But the requirements
so
at the moment,
there will be a property of uniformity. So I will show you an explicit example showing how things change when we change the size of a system. No, the index can take different values, but the way we have done it is in such a way that we can control what happens to the index.
Okay.
No? In the case of the Kita-F model, I will show you how the index jumps when you change, for instance, from a 3-side model to a 4-side model. No? Things, the Hamiltonian is the same or looks the same, but the index starts jumping. No? So we have kind of tried to introduce a way of controlling the index while we consider bigger and bigger sublattices.
Can I ask a question?
Yes, Val.
Andrés,
Yes.
The Araki-Woods calculation on going to the limit, okay, for a lattice, the final answer is sensitive to the way you take the limit. Okay? You get any typology for the polynomial algebra of observables. Yes. So here also similar things should be happening if you look at the appropriate algebra which is acting on your sublattice. Okay. So how does one control that, or is your index stable under these limits?
But what limit do you mean, Val?
The Araki-Woods calculation of constructing all the typologies of polynomial algebras as of hyperfinite polynomial algebras was starting from a finite lattice, states on that lattice, and taking the n going to limit, infinity limit in particular ways.
Yes.
So depending on how you took the limit, you get different answers.
Yes.
Now,
well,
sorry.
I mean, we have not studied those possibilities, but I can tell you, I mean, what I know. In our work, we have just worked with the self-dual algebra, regarded as a sister algebra, no?
Yeah.
And the computations are being done in the one particle Hilbert space, and that's what we do. Now, there are ways of obtaining different types of factors, and in this context of spin chains, for instance, or systems of that sort, Kyle, Matsui, and other people, they have studied the types that you get for instance, from the GNS representation of this ground state on now on a explicit representation, and there certain possibilities can appear, no? But this is not something I explored here.
Okay, I see that David is here, so he can answer it very well. Okay.
Okay. So so the construction of the automorphism goes in the following way. So we need this preliminary result. So we start with this family of Hamiltonians, no, which are continuous and differentiable along a path, and then let me denote with E plus S the spectral projection corresponding to the positive part of the spectrum of HS. Then the automorphisms we will construct, they satisfy this property. So somehow they allow us to shift the spectral projection at the point S to the spectral projection at the point S. So they are all connected. And this is what we use to show that the index has to remain constant. Now, the idea of the proof goes as follows. We can use the resolvent equation in order to define the derivative with respect to the parameter of these spectral projections. And then one shows that the derivative can be written in this form. So derivative is just a commutator. And if you look at this equation, then you realize that this is the same as working with the Kato version of geometric phases, no? So using families of projections, one can generate like a parallel transport, no? And this equation basically says that. Now, if you define the automorphism to be given by this expression, no, where V is the solution to this differential equation. So look at the operator D. No, the operator D can be given in detail. So then this unitary operator will generate the automorphism. Now, there is a result which I think also is due to Araki and Evans from their paper in '83, telling us that if we have a unitary operator which commutes with the conjugation and 1 minus the operator is a trace class operator, then this index, which I am writing here, is given by the determinant of V, no? So the only thing we need in order to apply this result is to show that 1 minus v is in fact a trace class operator. So this can be done using some types of estimates which are called Combes-Thomas estimates. And well, in this way we proceed and we can obtain this automorphism. So basically what we have done here is to study families of self-dual Hamiltonians along paths. These paths are continuous and differentiable, and the gap of the Hamiltonian remains open along the path. And then for the kind of Hamiltonians we have constructed out of limits of lattices, sublattices, then we can show that the index remains invariant, no? So it has to belong to the same class all along the path, and it has a uniform behavior with respect to the size of the system. So now I will come to the third part of the talk, which is has to do with our intention to try to generalize this to other situations, mainly the situation where we have not anymore a ground state described by a self-dual like a basis projection, but described by a symbol which corresponds to a thermal state. But before doing that, let me go down to specific examples which we have been working on and which display these properties quite well. So this first model is a very well-known one. This is called the XY chain. Here we have a one-dimensional chain of spins which have couplings of this sort. No? This model was in particular studied by Leaf, Mattis, and Schulz in their paper from the 60s, and there they introduced this way of treating spin Hamiltonians in terms of the Wigner-Jordan transformation. So it is possible to rewrite this Hamiltonian as a fermionic Hamiltonian. So if we choose this anisotropy parameter gamma to be equal to 1, what we get is the one-dimensional Ising model, which by means of the transfer matrix method represents the classical two-dimensional Hamiltonian. So it is a model that has been studied for many years. It is very well known. And the fermionic version by means of the Wigner-Jordan transformation takes this form. Now, regarding the remark by Denjo, you see that this Hamiltonian has terms of the form A dagger A and also A dagger A dagger. So its spectrum will depend, of course, on the choice of parameters. But if we write this in the self-dual form, the spectrum will be reflected and it will be more like duplicated. No? So we get this symmetry with respect to 0. Now, if we consider the XY chain as a system at 0 temperature, then it is known that there is a quantum phase transition especially when lambda is equal to 1, there is a phase transition there. So if you remember that figure I displayed at the beginning, there was a possible behavior going towards higher temperatures. In this case, this model does not have a thermal phase transition, but there is a quantum critical regime which can be studied. And even if there is no thermal phase transition, there is in fact a change of magnetic regime that depends on temperature. And this can be studied by considering the longitudinal magnetization, which is defined as this correlation function. It has to be defined carefully, because if you just try to compute the expectation value of sigma x, look at the operators here, no? So the magnetic field goes in the z axis. So that magnetization along the third axis is no problem, and you can compute it, but the magnetization along the x-axis, or the longitudinal magnetization, would give you 0 because of the C2 symmetry that the model has. So in order to define it properly, one has to proceed in this way. So you compute this correlation function, let n go to infinity, and then take the square root. And this is how this magnetization is defined. The computation boils down to the computation of this determinant in the limit when n goes to infinity. And the coefficients of the matrix are given by this expression. So here, lambda k is the energy in Fourier space. No? So once we diagonalize the Hamiltonian, we get a spectrum given by lambda k, and lambda and gamma are the original parameters in the Hamiltonian. So why am I mentioning this magnetization? Because what we have done is to compute explicitly, numerically, this magnetization, and we have shown that there is a coincidence between this behavior of the magnetization and a geometric phase, which in a sense generalizes the mode 2 index. So the mode 2 index has been defined in terms of basis projections, which describe the ground state of the system, so at 0 temperature. Now, using geometric phases, one can recover the value of the invariant at 0 temperature, but then one can have something else when the temperature is not 0. So this is why I am mentioning this magnetization. Now, there are experiments which can be modeled with Ising-like systems. So you see here, the axis has been reversed compared to what I showed you at the beginning. No? So here, temperature goes along the x-axis, and the parameter which is relevant for this system goes on the vertical line. But as you see, this system displays a ferromagnetic behavior in this region and a paramagnetic behavior in this other one. So it is for these kind of systems that I would like to be able to generalize the notion of topological invariant, so applying to these systems. If you follow the dashed line, then in the case of the Ising model, what we have is along the vertical axis for 0 temperature, there is a well-defined mode 2 index, which takes one value here from 0 to 40, and a different value from 40 to higher values. But if we just consider temperatures different from 0, we don't know how to define such a topological invariant. What one can do is to use Ullmann's definition of geometric phases for thermal states in order to come up with something which, if not topological, can be at least regarded as geometrical. So this is what we are interested in. But let me now show you how this mode 2 index appears in the context of the same model, but now with the interpretation of a fermionic model, which is called the Kitaev chain. So the model is just the same. Here you have this combination of fermionic operators, but now you regard the fermionic operators as real fermions sitting on a lattice, and this is the Kitaev chain. Now, for the Kitaev chain, we have an interesting behavior in terms of edge states. So we have two parameters, t and mu. So if you are sitting in the region which is shaded here, a representative point is this red one, then there will be edge states when you consider the system on an open lattice. So with open boundary conditions, you will have edge states which are due to the fact that there are Majorana modes, no, on the edges. When you decompose the fermionic operators, thinking about just a real and imaginary decomposition of these operators, this would lead to Clifford algebra generators, which can be called Majorana operators. So when you decompose the fermionic operators in that way, you will see that each fermionic operator contains two Majorana operators. And when you are sitting in this shaded region, precisely at the point where the point is red, the coupling between the Majorana operators on the edges disappears, and you are left with two modes which produce these edge states. So there are zero modes related to that. And the other regime is the regime outside the shaded region. One of these representative points is the blue one here. There will be no edge states. So the description of the system, according to whether it has edge states or not, can be given in terms of a topological invariant, which in this case is just the same mode 2 index I was telling you about. But Kitaev gave a definition of this index in terms of the parity of the ground state, and one can show that these two definitions just agree. So now let me show you what one can do for a explicit computation of that index. So here I am doing the following, I am proceeding in the following way. I am considering finite lattices just to illustrate what is going on. The diagram is a diagram where the horizontal axis is the parameter t and the vertical axis is the parameter mu, so it should coincide with this. But I am also considering boundary conditions. So I introduce a parameter r, which has the following meaning. If r is equal to 0, then I am considering the chain with open boundary conditions. If r is equal to 1, then the system is being considered with periodic boundary conditions, so it is a closed system. Now, according to the bulk edge correspondence, or what the bulk edge correspondence says is that you compute the invariant for the closed system, and it tells you something about what is happening on the edge for the system with open boundary conditions. So, as you see in the first 3 plots labeled by A, B, and C, what I am doing is to keeping a chain with just 4 sides, but I am starting with open boundary conditions, and then I start to close the boundary, and already for r equals 0.2, you see that the region, the shaded region, starts resembling what would happen in the fully closed case. So this white region starts to disappear, no, and you get here. Now, what happens if I keep increasing the number of sides, but I keep open boundary conditions? If I have open boundary conditions, then the index can be, can be computed, but it does not reflect what is happening on the edge. No, according to the bulk edge correspondence, this makes sense, and this leads me to the remark I made to Denjo. You see that if I take n equal to 2, the index has this behavior, and for the same set of values of the parameters t and mu, if I just add 2 more sides with the same conditions, then the index changes in this way. So it has a very complicated behavior as I change the lattice size. In any case, if we are to comply to the idea of the bulk edge correspondence, one would have to compute this always in the periodic case, so taking r equal to 1, so it would look more like the top right figure, no? So this index can be computed, and it is well understood, but what we want to do is to see if we can now go to the finite temperature situation. Now, regarding the finite temperature situation, then I am led to the question of how can I lead with edge states if I have temperature? So there are several ways of studying edge states for the Majorana case, which I am discussing now, and these are the following. So you decompose the fermionic operators in terms of Majorana operators. So these are just Clifford algebra generators. I call them gamma A and gamma B. If you take the Hamiltonian in diagonal form, then the coefficients of the Bogoliubov transformation that diagonalize the Hamiltonian. Since this work has been done numerically, I am right now considering finite systems. So the coefficients of the Bogoliubov transformations will be given here by matrices phi and psi. If I go to the thermodynamic limit and go back to the self-dual approach, these phi and psi coefficients would become operators, and they will be pieces from which I can construct this unitary I was calling Bogoliubov transformation. Now, how do I detect the presence of edge states? Well, I can compute several types of correlation functions. For instance, you can compute an edge-to-edge correlation function, taking the type A Majorana operator on one edge times the type B Majorana operator on the other side of the system, and this will tell you about the existence of edge states when t is equal to 0. But if you want to have something sensible for t greater than 0, you have to be careful. So what I have used is this version where I take the Majorana wave function, so to say, no. So it is this type of correlation function that will tell you about the existence of edge states. So just to illustrate what happens here, let me show you plots of these correlation functions, which boil down to, if you see these expressions, it boils down to plotting the coefficients phi and psi, no? So the coefficients of the type phi 1k, they are displayed in blue color. I have a chain of 60 sides, and for this choice of parameters, mu equal 1.1 and t equal to delta equal to 1, the mode 2 index equals to 1. What happens here? There are no edge states. So this wave function is somehow, I mean, it vanishes toward the edges and it is centered around 30 more or less. But if I change the parameters a bit, so you see here, I am entering this shadowed region we were discussing before, then very quickly, you see that these states get localized toward the edges, no? So this is actually a suitable definition of edge states in terms of those correlation functions. So what I want to do now is to see what happens if I still work with this correlation function, but now I compute not the ground state correlation function, but the thermal expectation value. And what will happen is that, well, if I keep increasing the number of sites, of course, the states get more and more localized. So if I start increasing temperature, you will see a behavior of this type, no? So now I only keep one of the modes, the one that localizes towards the left side of the chain, and I display in blue color what happens at t equals 0, and in red color what happens in this case at t equal 0.1 in the units I am using. So what you see is a change in behavior. Look what happens if I increase a bit the temperature. Then I could still talk about a localized state on the edge, but there is some delocalization now which starts appearing. The change will not be an abrupt one, but anyway, you can say we still can talk about something on the edge, and at some point you will definitely not be able to talk about edge states. So if I keep increasing the temperature, then this edge effect will be washed away completely. Okay, so with this, well, what we want to do now is to have a geometric tool that allows us to say something about these edge states and about the magnetization I was discussing before. Then how much time do I have? Perhaps is
we tend to be relaxed about
okay.
time. Sorry.
So this is the third part. It will require a couple of definitions, but it won't take much time.
That's fine. That's no problem.
So in this, so what I have discussed now is for the XY chain, we can compute the longitudinal magnetization. It has a certain behavior. One can have numerical control over that computation. And there are experiments that show that it is quite interesting to consider that change of magnetic regime. And in the interpretation of that model as a key-type chain, well, there is this presence or not of the Majorana edge modes. And we know that the mode 2 index can be used to characterize whether there is whether there are Majorana states or not on the edge. So now, how are we going to deal with the finite temperature case? So what we are going to do is to consider a kind of generalization of the geometric phase or Berry phase, which can be applied to states which are not pure. In this context, I mean, this can be defined properly in the infinite dimensional case, but because of the subtleties related to the geometric construction in infinite dimensions, I will just discuss the finite dimensional case. So in this case, let me consider a family of density matrices. So if we have a family of density matrices, I would like a family like a path of density matrices. I would like to consider, for instance, closed loops of density matrices and ask the question whether is it possible to compute a kind of holonomy in that case. This is what we do when we compute Berry phases, no? So how can we generalize this for paths of density matrices? So the construction is quite interesting. You start with the composition of the density matrix in terms of, you can consider the spectral projection, and then you can purify this. No? In this context, the purification works quite easily. You just take the eigenvalues lambda I, they are positive or non-negative at least, so you take square roots, and if you have used projections which are given by this expression pi, no, then you construct a basis in a doubled Hilbert space, now doubled in the sense of tensor product, and this will be a pure state which has the property that when restricted to the first Hilbert space will give back the original density matrix. So this is a purification of the state. In the infinite dimensional setting, well, you can, if you have such a state, this state will perhaps be described in the context of quasi-free fermions by a symbol. So you can just consider the GNS construction related to that state, and in the GNS space you will have a cyclic vector which is pure, representing your state. No? So that's another possibility. So here you see that there is a redundancy, or yes, we can call it redundancy. This purification is not unique, basically because it is only when we restrict this state to the first subsystem that we get back our original density matrix. So if we multiply the second entry here in equation 4 by a unitary operator, we will still get the same density matrix. So this appears to be like a gauge symmetry. No? So now let me define a modified pure state psi u by multiplying with a unitary operator here. Now, when I compute the density matrix coming out of tracing out over this state, I will get the same one. So the idea then is to think of this triple. M is the space of density matrices. In order to have a well-defined bundle structure, I will restrict to really positive elements. And then with this projection, we get a fiber bundle structure with gauge group U of H. Now we can make use of this isomorphism between H tensor, H dual, and the Hilbert-Schmidt operators to define a connection, basically using the inner product in the Hilbert-Schmidt space.
Sorry, I'm slightly confused as to what U is doing here. You have a sum over I, but you've insisted that U is I independent?
Exactly. So you let
So-
U act on EI on the right here.
Okay.
So now so this vector is defined on H tensor H.
Yes.
So trace out the part that corresponds to the second factor. If you do that, then you will get a density matrix, which is exactly the same one for any choice of U. So it does not depend on you.
This I understand, but it is acting on H is the full Hilbert space, which includes all of I, or you're talking about an H which is just sitting at one site. The sum here is over sites.
Yes, well, but what we don't have sites anymore. I mean, this is
there's an index here, I, and there's
exactly.
a sum on it. But,
exactly. So let us go back here. I consider a finite dimensional Hilbert space.
Yes.
And I pick a basis, which is the one diagonalizing the density matrix, so to say.
That's fine.
But so now the statement is that I can get a purification of this state just by this formula. But well, of course, I have to go to H tensor H.
Yes, but I would have thought that H would rotate the index I. Or I would have thought that U would rotate the index I.
Well, it will
doesn't.
make it change, but it doesn't. No, so you just let it act on each EI, on each one of them.
Okay.
In which, yes, of course. It only acts, I mean, it is acting on each EI, but then when you compute the trace, you will get the same density matrix.
Yes.
So this gives this gauge structure. And well, if you implement it suitably, you will get a generalization of very phase to mixed states. So how this is done? There are works from several people. One of them is Ullmann in '86, but there is a version which is equivalent to Ullmann's, which I like a lot, and this is due to Grosse and Dabrowski. For me, it is more intuitive from a geometrical point of view. So I will present that one. So what you do is, first, let us restrict to just positive or invertible density operators. Now, the right action of these unitaries on H tensor H preserves the scalar product. So that's a fact. And now, since I will work with positive elements, I will just, here the isomorphism is between H and H dual, but I will just do something similar between H tensor H and Hilbert-Schmidt operators. Basically, if I have an element in H tensor H written in this form, I just swap the ket in the second expression to get a ket-bra type of expression, and this will be a Hilbert-Schmidt operator. Now, the norm of this vector in H tensor H will coincide with the Hilbert-Schmidt norm of this vector in this space. So we will make use of that, and now we define a total space to be given by the inverse image of the projection, which is a subspace of the Hilbert-Schmidt operators. So now our total space is something which is living in the space of Hilbert-Schmidt operators, and the basis manifold is just the space of invertible density operators. So I don't want zeros for the eigenvalues of the density matrix. So now the right action of G, so the unitary group of H on P, will be defined just like this, no? So just right action. And then we will have a well-defined notion of vertical spaces because we have the projection. And we can therefore characterize the vertical space in terms of the tangent space. Here we have a Hilbert-Schmidt operator, so the tangent spaces are just the space itself, and we can characterize the vertical space at A by this condition. So it is the set of elements of the form AS, where S is anti-skew. Now, the vertical spaces are induced by the projection. Now, giving a horizontal space amounts to define a connection. So what is the connection we are going to work with? The connection will be induced by the metric structure that we have here. But one has to be careful. It is not the inner product in the Hilbert space or in the Hilbert-Schmidt space. It is the symmetric part. So the Riemannian structure, a part of the Hilbert-Schmidt product, meaning we have to take this combination. So this Riemannian structure will allow us to define what we mean by horizontal. So a vector will be horizontal if it is perpendicular to the vertical space in the sense of this metric structure. And this defines a family of horizontal spaces that behaves in the proper way with respect to the action of the gauge group. So we actually have a connection. So one can check all this, that it will define a connection. And then using this connection, one can study the problem of lifting a curve of density matrices, a path of density matrices to the total space. So let me call rho of T the path of density matrices, then a horizontal lift A of T. It can be shown. It has to be a solution to these two differential equations. No? Now, these equations can be simplified to this one, A dot equal to TA, a first order differential equation, where T is given by this expression. So the lambda i's are the eigenvalues of the density matrix. The pi's are the projections. So here recall that we had this decomposition, and we have information about rho dot, so the derivative of rho. Well, something which is nice, for instance, is that you can compute the usual Berry phase for a spin coupled to a magnetic field. We know very well how to compute the Berry phase in that case. If you do the computation, thinking that you have now this system embedded in a bath of certain temperature, then you can get a holonomy matrix. Now, if you compute the eigenvalues of the holonomy matrix and take the limit to 0 temperature, you will exactly recover Berry phases. No? And this is not trivial because the bundle is not defined on the edges. If you go to the edge, you will have projectors and you will be in trouble. No? But somehow, for this particular connection, from the physical point of view, it is quite interesting because you will get Berry phase when you consider that limit. So here we have a computation of this Ullmann phase or geometric phase for system with temperature in the Dabrowski-Grosse formulation. It is a little small here, but here we have the magnetic field for the XY model, and here in the vertical axis we have the temperature. So this is a computation that can be done in several ways. People like Villuela and Martin Martinez have done these computations of a geometric phase for the XY chain.
And you've taken, if I can read correctly, you've taken gamma equals 1, which corresponded to the Ising model.
Exactly. So here, yes, I have taken gamma equal 1, and here you have the quantum phase transition. So if you consider only the horizontal line here, the C2 index would give you +1 here and -1 here, or the other way around. No? So there is a topological index we can compute at 0 temperature. Now, as you see, the computation of this holonomy, now the holonomy can be anything, no? But in this case, it is only plus or minus 1. And this is interesting because it coincides with the value of the invariant at 0 temperature, but it can be computed also for higher temperatures, and we get this behavior. Now, the computation that Villuela and Martin Martinez and colleagues have done is a computation using the density matrix for that model. What we have done is a computation not using the density matrix, but the symbol that leads to the thermal state, this kind of symbol I was talking about at the beginning of the talk. The two computations coincide for this model, but they will not coincide for more general situations. And we think it is more sensible to use the symbol than the density matrix. But well, this is yet to be seen in more general situations. Now, what we have done, is to also compute the magnetization, and we have found that the magnetization curve, the change of regime for the longitudinal magnetizations between paramagnetic and ferromagnetic behavior exactly coincides with this curve. So here you see what happens, for instance, for a temperature of 0.1, when we start letting the system size increase. You have to take into account that this computation has been done numerically. So, well, taking the limit is not that easy. But you see that as we keep increasing the number of sites, then actually the magnetization vanishes at exactly that point. No, so it is quite interesting to see what happens. Here we have a 3D image of what happens. So the green line is a level set for this magnetization curve, and it resembles what is going on with the geometric phase. So far for the magnetization, but now what some people have said about the edge states is that there is no way of capturing what happens with the edge states using this kind of geometric phase. Well, here I have a plot. This is still a preliminary result, but I have a plot not of magnetization. Now I have moved to the Kita-F chain, and I am comparing a computation of the geometric phase. The vertical axis is temperature, and the horizontal one, it is one of the parameters in the Hamiltonian. So these two colors gives us a sense of whether there are edge states or not. Now, remember that when I plotted the edge states for different temperatures, we saw that there is no abrupt change in the behavior. No, at some point you say there cannot be edge effects anymore, so it is kind of blurred, no, as you see here. So what I have done is to define a quantity that allows me more or less to distinguish whether the edge states are still surviving temperature or not. But you see that the behavior is quite nice. I am calling this melting of edge states because of a paper of Harald Grosse and colleagues from the 80s, where they studied anomalies, and they were asking whether anomalies would depend on temperature or not. And this is not a casual remark, because for other types of systems, these invariants are related to Schwinger cocycles, and Schwinger cocycles are related to anomalies. So there are certain cases where the anomalies survive temperature and others in which they just disappear. So I think that studying this type of properties for models where the topological invariance at zero temperature can be given in terms of Schwinger cocycles and the like, it would be interesting to see what happens now when we put temperature. And then let me go to the final statement for this talk, which is that the way we have computed these phases is in terms of the symbols. The symbol describing a thermal state in our context is given by this expression. So it is a positive operator, and by Fourier transformation, we get a family of operators of this sort, which can be considered as a path in momentum space. So this is the way we compute the geometric phase. Now, what we have found, which is quite interesting for me, is that if you purify the state, so maybe using the GNS construction, for instance, then there is a way, and older works by Araki and other people showed how to express the purification corresponding to this symbol in terms of basis projection. So if you purify the state given by this symbol, you go to a bigger Hilbert space, there will be a basis projection which purifies this state. Now, this is very interesting because if you have a family of basis projections, then you can compute the geometric phase in the usual way, like in the Kato or the Berry approach. We have done that in our models, and it turns out that the two computations coincide, namely the geometric phase for positive operators, which are mixed states, and the geometric phase for this family of projections. And now, it is interesting because the mode 2 index was defined for the families of for self-dual projections. No, now unfortunately, if we go and try to compute the mode 2 index for these projections, we get 0. No, I mean we are still trying to understand what we have not seen yet, but it is a hint that it might be possible to define such indices in situations where the thermal properties are interesting. No, so with that, I would end my talk. So thank you very much for your attention.
Okay, thank you very much, Andrés. Questions?
Andrés, this looks to me very similar to Tomita Takesaki, this Ullmann thing.
Yes.
So it looks to me that what is done is to change the operator J.
Yes.
By a unitary transformation, because that establishes a connection between A and this commutant.
Yes, Val, you're absolutely right. In fact, it was Soad in his PhD thesis. She did that precisely, no, because of our work, no, Val, with on Tomita Takesaki for this matrix systems. Then, well, she was trying to get an understanding of thermofield dynamics by means of Tomita Takesaki, no? And then, well, we started to try out different things, and then we realized that, I mean, that it was possible to work with this purification, and there you can compute the usual Berry phase, and the two results do coincide. So we are trying to see how general that is, but I think it's fairly, I mean, the chances are high that it is quite general.
So what is, if I understand correctly, what is happening is that the commutant of the original algebra is actually, because you can make, what is it, automorphisms of that commutant, okay, without changing the first one, is giving you a fiber bundle structure.
Exactly. So actually,
yes,
this is, you remember, Val, that this is what we were discussing when we were doing that work with Ivan and so on. We had in mind some application of Berry phases in that context because of the entropy increase. No? But I mean, I was unable to get something out of it, but it turned out to be a good idea to apply it to these systems. So this is how it came about.
Just one remark. I think that this is very closely related to what Doppler Haag-Roberts say as transportable endomorphisms. You remember that they have they can actually move the algebra in some region to another one by an endomorphism, which is given by the Kunz algebra, appropriately defined. You remember, no?
Yes, but
sorry.
Yes, I don't see it in this context, but maybe that's true.
Yeah, because that does give a connection on the algebra, because you can move it around, okay? And that identifies a connection, but I think it is not unique. Okay, I mean, since you have brought it up, I don't think it is unique, and that may give a connection also. The choice of this, in fact, it has to be like that, because when you go around, it gives you the spin statistics theorem.
Okay,
it has to be that they already proved. Okay, it has to be. By the way, we should discuss.
Yes, sure.
I found out, this is something you may know, okay, just asking, that if you have, it's quite easy to prove, David is there, okay, that if you have C-star algebras, okay, and you consider an isomorphism of the C-star algebra to another C-star algebra, it is necessarily an isometry. That is quite easy to prove, I think, using the condition on the norm. Okay, Either it is norm decreasing or it keeps the norm fixed. If it's an isomorphism, it keeps it fixed. And it is then an isometry. Okay. Then this is something you may know. That if this system algebra is simple, I think that is the case with for the kind of thing in quantum field theory. Then I think this, I'm not sure, that it is necessarily given by the Kunz algebra or some factor thereof, some quotient thereof. Because the Kunz algebra is universal. I think. So this is what Sergio Doppler and Haag-Roberts were doing, you know. They were using Kunz algebras. Here I am not very clear. I am not sure because this came up here. Okay, so I was thinking. But this is what you're doing is very interesting because I think that should be possible to get more general indices, not just Z2, but much more general ones.
Yes, yes. This is why I mentioned that that talk by Chris Bourne last year when he made me aware of an approach to the periodic table of topological insulators, where one actually starts from this mode 2 index, and then when you start adding symmetries, then this can be made more finer. I mean, you can refine it, and then all other indices appear. But I have not studied that, but it looks like a very nice thing to do.
Sorry, I have a question about this because it's a little bit strange that you can define really everything from the Z2. I mean, the Chern classes are not Z2 numbers, right? So, I mean, there is a lot of, the periodic table is actually very big. It is even bigger than the original one nowadays, because we can add the crystalline symmetry, the discrete symmetry. So, you know, even with interaction, we get Z8 to Z16. So, not really clear how this can be really done starting from Z2 that you mentioned.
Yes. It is. Yes, it was surprising to me, but there is a. I mean, the idea is you start with that one, but then you say, okay, we have to refine it, and what he said was, well, using KK theory, you can understand that how that appears. I have the reference. I can send it to you.
Yeah, please.
I have not studied that paper, but I think it's. I mean, it's. For me, it's interesting because of my work on with this mode 2 index, no? So
right. Maybe also I have another couple of questions. So so you discussed the Z2 that is basically related to Kitaev in one way. But there are also other Z2, you know, in 2 dimension, there is the Kane-Mele, and also derive this one from your approach, from your algebraic approach. I mean, from K-theory, I know that it's possible, but I'm following your way.
Yes, I mean, in that case, for instance, as you were saying, no, so this type of C2 index is special in the sense that it is not actually the index, for instance, of a Fredholm operator. There is a Fredholm operator there, but you use it to show that the dimension is finite, and then you just define the index to be I mean, in terms of whether that space is even or odd. But these other indexes are actually coming from, let me call it, local curvature terms. No, so you integrate something like that in the case. But the formalism, I mean, using, for instance, the operator theory approach, you can compute those and those topological invariants using K-theory, using Chern numbers in the way they are defined in non-commutative geometry, for instance, and then they can be computed. Now, my question, and this is something we have to do, is, well, this is well known, no, how to compute these invariants, but my question is, can we generalize that to finite temperatures, for instance?
Yeah, this is very interesting because there was a lot of debates in the community. I'm a condenser matter, by the way. So so there is a lot of debates, really, how really if you know, topological invariant at finite temperature are well defined. So even the Ullmann phase that you mentioned actually is a little bit subtle. So of course it's a geometric phase, but some people claim that it's topologically trivial.
That was, yes.
Right. So they criticize a little bit what so Martin Delgado and Vihuela
Yes.
did.
Yeah, I said Martin Martinez. It is Martin Delgado.
Yeah, Martin Delgado. Yeah, yeah.
Martin
no.
Martinez works in
Right. So no, because actually again there is a problem of so it's a little bit subtle, as I said, the topology. So that's why people are nowadays taking another direction, I have to say, even because if you want to write in 2 dimension, it's I think the Ullmann really, you know, if I remember, one of their paper was about, you know, to calculate the Chern number at finite temperature.
Yes.
But they end up doing that. Basically, it's not quantized anymore. So they, I mean, it's not, it cannot be not quantized. So if you're not quantized, it's not a quantity, right? So that's why also in your plot, I mean, it's a little bit, you know, it's a delicate story, right?
Yes. Yes. So that's why, I mean, that last part is just work in progress, no? There are hints, no? For instance, the fact that if you compute the holonomy for the mixed state, and you get the same result as if you purify the state and then compute the vary phase. So there, if you can compute a vary phase, you can perhaps compute Chern-like numbers, which are well defined mathematically. Because the problem in the literature is that people compute certain numbers and they call them topological, but you have to prove that they are
exactly.
That's the problem. So this is one of my motivations, not to try to get something of that type.
All right. Okay, so sounds good. Thanks.
Okay, thank you.
Can I make a remark? Then I quit. This is just I am sort of seized by what has been done in quantum field theory. Okay? There, the question of you talked about finite temperature. But every local algebra is a KMS state, automatically. The KMS Hamiltonian depends upon a particular local algebra, but it is always a KMS, again, because of Tomita Takesaki. So that is not an issue. And they, depending on the particular topology of the underlying spacetime, they also get the break group. Okay? So I think there is some connection between what you are saying and what has been done there. You're also getting C-star algebras, no? So
yes,
if the C-star, so I have to go now. I'll talk to you later.
Okay, sure.
Unfortunately, Indra is calling, so I have to go.
Okay,
just to keep my reputation, I have to go. Okay. Ciao, bye.
All right, take care, Bob.
Hello.
Are there other questions? Hi, Val, you're still there, I think.
I'm leaving.
Okay.
I left.
I have a quick question, which is probably trivial.
Right.
I mean, but I'm not familiar with this stuff. And David probably knows all this stuff. I mean, he knows this stuff very well. Val mentioned this to Tomita. A couple of days ago, I was on Jordan algebras and these different types of Jordan algebras, and a Tomita projector, a Tomita operator was, sorry, not projector, a Tomita operator was defined, which is an involution. Is your gamma a Tomita operator?
No. The gamma I was mentioning before.
It was an involution. It's complex. It's anti.
Yes. No, it is. I mean, it is anti-linear, but it is not the Tomita operator. The Tomita operator you would get in this context here just by defining a map, which sends, and you start with the algebra, and you regard elements in the algebra as vectors, no? And then you define a map by sending an element to its conjugate, and then you will get an operator S, and then you get the conjugation J. So it is hidden here in this expression, in these expressions here, equation 4. It will produce, I mean, this antilinear map will allow you to go from the algebra corresponding to the first factor to the algebra corresponding to the second one. We have not used it here, but it is related to that one. No?
Okay. And this talk I was at was, I mean, Boggle-Ubov transformations were mentioned, but in the context of Hawking radiation. And I think these two H's would be the quantum states in the two causally disconnected sets.
Excuse me, can you repeat the question?
This talk I was at, I mean, this was mentioned in the context of Bogoliubov transformations and Hawking radiation.
Okay.
And the two H's, I think, would be the Hilbert spaces in the two disconnected parts.
Yes. I think, yes, there is a, I mean, there must be a connection mathematically, at least, no? Because you have, I mean, you want to describe two subsystems, no? Here, we are doing it in the other direction. So we start with a system described by a mixed state, and then while purifying it, we are trying to model what we have in terms of two subsystems which are coupled, which are given by this H tensor H. No? So you can also think in those terms.
Thanks.
Do we have other questions? If not, then I'm just going to stop the recording and we can
Okay.
take it more easily. Okay.